So there's a couple things going on in this particular question. You've got a pencil measured in centimeters, but then they want to know how many millimeters long would it be, is what they're talking about at the beginning of the second line there of text. So we've got that conversion that's happening there, but we can do that. And then they've also talking about not just one of those pencils, but 10,000 pencils. So we're multiplying this by 10,000, and then we're expected to somehow convert that giant question into a scientific notation type question. So the first thing they tackle there is the conversion into millimeters. They remind us that 1 centimeter is 10 millimeters, so that 18.7 centimeters is the same as 187 millimeters. Remember, we've already seen multiple times in our mathematical careers that list of metric prefixes, which helps us convert. Starts off with kilo, hecto, deca, then goes to the unit, which is where I'll start the chart. The chart starts at meters. And then goes to deci, centa, and milli. Well, in this particular question, we were converting from centimeters to millimeters, which on our chart is one jump to the right. So to change that in terms of the decimals, then we also do the same thing with the decimal and move it one time to the right. So our 18.7 centimeters becomes 187 millimeters. Okay, but it's not just one pencil, it's actually 10,000 pencils. So we're taking this 187 millimeters and multiplying it by 10,000 for the 10,000 pencils. Well, when we do that, we get a solution of 1,870,000. And what we're going to do now is convert this into scientific notation using the same approach that we used earlier. So we're going to take and drop the decimal in here somewhere, so this becomes something between 1 and 10. Well, we know that that is between the 1 and the 8, because 1.87 or 1.870, or however you want to write it, that is indeed between 1 and 10. It's always times 10, because again, our numbering system revolves around the number 10, and then we just have to figure out our exponent. Since this is not a decimal, the exponent is going to be positive here, and we're figuring out how many times we move the decimal to make that happen. As you can see in this particular question, the decimal was moved 6 times to make that happen. So we got 1.87 times 10 to the 6. And that's going to be 18.7 centimeter long pencil laid 10,000 end to end is 1.87 times 10 to the 6 millimeters, having converted that as they instructed us at the beginning. All right, let's go ahead and take a look at the next question here. Number 4, a certain cell has a diameter of approximately 4.11 times 10 to the negative 5th meters. A second has a diameter of 1.5 times 10 to the negative 5th meters. Which cell has a greater diameter? So this is all about me comparing numbers without spending the time of converting these into regular numbers, which is just going to be time consuming. Hopefully you remember from last year that when we have the same exponents, what we do to compare these things is we look at the numerical part of that scientific notation question. If the exponents are different, it's really easy, because whichever one is bigger is going to be the bigger number. What's different about this particular question, though, is that the exponents here are negative. So we have to think about how the negatives are going to impact us here, because of course the negative exponent indicates that what's going to be generated here is a decimal. So we're comparing 411 and 1.5, both going to the negative 5th power. Well, let's go ahead and turn those so we can see here what those are going to look like, but you'll see that those rules are still going to apply here. I'm going to kick this 5 times to the right, and I'm going to kick this one also 5 times to the right. So that's 0.000411 versus 0.000015. Well, as you can see, even though it's decimal, 411 is the way this is written in comparison, still works out to be bigger than the 15. So since the 411 part is larger, that means the first cell has a greater diameter. So again, we compare the exponents. If the exponents aren't a dead giveaway, then we go to the numerical part in front, and that's how we do our comparison. All right, so number 1, writing the number in standard notation, 1.9 times 10 to the negative 5th. Again, when that is a negative exponent, that means we're going to kick that decimal to the left to generate that in standard notation. So since the exponent here is negative 5, that means I'm going to move that 5 times to the right. And again, all those empty jumps, those are going to fill in with zeros. So we end up with 000019. Number 2, we're writing 0.000811 in scientific notation. Well, again, we want to drop the decimal in, so this becomes something between 1 and 10. So that means after the 8 and before the first 1, that's going to give me 8.11, which is going to make that happen. Scientific notation always continues then with a times 10, again, because our numbering system revolves around the number 10. And then the exponent is how many times we move the decimal to make that happen. Since this was a decimal, again, in order to make this happen, that means the exponent is going to have to be negative. We moved it 1, 2, 3, 4 times to the right, so the exponent ends up being negative 4. 8.11 times 10 to the negative 4. Number 3, an oil rig can hoist 2,400,000 pounds with its main derrick. It distributes the weight evenly between 8 wire cables. What is the weight that each wire cable can hold? Write the answer in scientific notation.